Hi, Dr.
Hi, Dr. Cho.
Oh, hey Oliver and Colin. What would you call it when Emily relaxed in a chair and she also had a pet feline?
Emily sitting plus kitten?
No, it's M-sat plus cat.
Oh.
Now, this formula is an important part of calorimetry, and calorimetry is a process that chemists use to determine the heat energy of a chemical reaction based on temperature changes. And we usually do this with a device called a calorimeter. Now, this technique is useful for understanding how much energy is contained in a particular reaction or substance. You know, the calories label on your Cheetos bag, that number is determined with calorimetry. Calorimetry is literally all around us. To learn how calorimetry works, we first need to understand the thermodynamic properties of delta H and Q. Now, can someone tell me what delta H is? Yeah, Oliver.
Delta H is the amount of heat energy the system gains or loses during a reaction.
Exactly right. Yeah, delta H stands for enthalpy, and it's per 1 molar chemical reaction. What a tremendous answer. So now, what would it mean if delta H is positive or if it's negative? Yeah, Colin?
I think if delta H is positive, it gains energy into the surroundings, and if it's negative, it releases energy into the surroundings.
Another perfect answer. Oh my god, you guys rock. So, delta H is usually measured in terms of kilojoules per mole of reaction. Now, let's talk about Q, this constant right here. Q represents the total amount of heat energy gained or lost by the surroundings of a reaction. That's important, the surroundings, you guys. Now, according to the first law of thermodynamics, energy can neither be created nor destroyed. Therefore, the change in heat energy of the surroundings must be equal and opposite to the change in heat energy of the system, assuming a perfect transfer of heat. In other words, we get this relationship. Delta H equals negative Q. Now, I mentioned that delta H is the amount of heat per 1 mole of reaction, while Q represents the total change in heat energy for the surroundings. What would we have to do to the Q value to get delta H?
We would have to divide the negative Q by the moles of the reaction.
Fantastic, you guys are on a roll today. Exactly right, that would yield this equation. Delta H equals negative Q per moles of reaction. So, now back to calorimetry. It's the experimental process by which we can calculate these values. So I'm going to play an instructional video for you guys for the lab that we'll be doing today.
This video is brought to you by the Royal Science Academy. In this video, we will be departing upon you the knowledge of the basic laboratory procedures for a calorimetry experiment. This here is a calorimeter. It's a vessel that measures the change in temperature of a chemical reaction. As you can see, it is heavily insulated to keep the heat energy inside the calorimeter, and it contains a space for the reaction to take place.
A process that calorimetry is often used for is determining the calories of a specific type of food. Today, we shall fill this calorimeter with water, H2O as I personally like to call it. Under the calorimetry apparatus, we will ignite a marshmallow. As the marshmallow burns, it will heat up the water in the calorimeter, and we can quite easily measure its temperature change as the reaction progresses. Calories are simply a measurement of energy, and so if we calculate the value of Q from the temperature change of the water, we can determine the number of calories contained in this marshmallow. Q can be calculated using the equation Q equals MSAT plus cat, or MSAT for our purposes. M will be the mass of everything inside of the calorimeter, S is the specific heat of water, 4.186 joules over grams degrees Celsius, and delta T is the change in temperature of the contents of the calorimeter in degrees Celsius.
Here are some safety tips. 1. Make sure your marshmallow is organic and sustainably grown, an A+ grade.
A hot calorimeter looks like a cold calorimeter. Wowza!
Now, although it's tempting, but don't play with fire. Wow, those two scientists look like Brad Pitt and Leonardo DiCaprio.
They look kind of familiar, don't you think?
I think so.
Alright, so as you guys saw in that wonderful video, calorimetry can be used to determine how much energy is stored in your food. Calories, anyone? So that's what we're going to be doing in the lab today. So as a sample, we have this beautiful, nicely delicious, fluffy marshmallow. And by burning this marshmallow in this calorimeter, we will be able to find the Q value, the total energy released, and from that we can calculate the calories per gram.
I measured the temperature change of water to be 1.5 degrees Celsius. However, under relatively good lab conditions, which we certainly did not create, the observed temperature change will be smaller, around 0.0786 degrees Celsius. Our value is too big, possibly because the Bunsen burner, and not just the marshmallow, unintentionally raised the temperature of the water. To find Q, you can then plug in the mass of the water in the calorimeter, the specific heat of water, and the temperature change into the equation Q equals m set. This gives you a Q value of 2.011 joules.
We can divide this value by the grams of marshmallow that actually burned, 0.13 grams, to find the joules released per gram of marshmallow burned, 15.47 joules per gram. If you multiply this by the mass of the original marshmallow, this will give you the total joules released from burning the entire marshmallow, about 79.51 joules. Lastly, we can convert this value to calories through the conversion 1 calorie equals 4.184 joules. By dividing our value of joules by 4.184 then, we can now determine that this marshmallow had around 19 calories.
Wait, but online it says a marshmallow is 23 calories. Why didn't we get that, Dr. Cho?
Well, that's because when we did our experiment, we didn't have a perfectly insulated calorimeter. This means that some of the heat escaped from the burning marshmallow and into the surrounding air. It didn't go directly into the water, which lowered the change in temperature, or delta T, and gave us a value of the calories a little bit too small than what you found online. Also, since the calorimeter wasn't perfectly insulated itself, it was a nice, beautiful LaCroix bottle, or can, some heat energy may have been able to escape through the container and into the surroundings, also lowering the value of delta T.
Wow, we learned so much today, Dr. Cho.
What?
Wow, from now I'm gonna burn all of my food.